Hello everyone, today we'll talk about data-driven leakage detection and intervention planning. This course builds on the pressure management concepts introduced in the previous course and shifts the focus toward data-driven leakage detection and intervention planning. While pressure control is an essential foundation, it is often not sufficient on its own to fully understand and manage water losses in complex urban networks. Data plays a critical role in identifying, analyzing, and prioritizing leakage issues. Traditional approaches that rely on visual inspections or reactive responses are limited in their ability to detect hidden or slowly developing leaks. Data-driven methods enable continuous monitoring and systematic analysis of network behavior. By the end of this course, learners will understand the key concepts behind data-driven leakage detection and how analytical insights support effective intervention planning. The course also emphasizes the connection between analytical processes and field operations, preparing learners for practical implementation in real-world water network management. Pressure management is a powerful tool for reducing water losses, but it has important limitations. Not all leaks are directly linked to pressure levels, and some losses develop gradually without causing immediate pressure anomalies. As a result, relying solely on pressure control may leave certain leakage issues undetected. Monitoring and analytics extend the capabilities of traditional pressure-based approaches. By continuously observing network behavior, utilities can identify patterns, trends, and deviations that indicate potential leakage. This analytical perspective allows for earlier and more accurate detection of problems. The transition to data-driven methods involves combining pressure data with other data sources such as flow measurements and consumption records. This integrated approach shifts water loss management from reactive responses toward proactive, evidence-based decision-making. In data-driven leakage management, the International Water Association Water Balance Framework provides a structured approach. Non-revenue water is calculated as the difference between system input volume and billed authorized consumption. Within this framework, real losses represent physical leakages, while apparent losses relate to metering and billing inaccuracies. This structure enables measurable DMA-level performance evaluation. Data-driven leakage detection relies on the integration of multiple data types that describe different aspects of network behavior. Flow and pressure data provide real-time or near-real-time information about how water moves through the network and how pressure conditions change over time. Consumption and meter data offer insight into expected water usage patterns. By comparing measured flow with consumption records, utilities can identify discrepancies that may indicate leakage. Smart meters and billing data are particularly valuable for understanding demand behavior at different temporal and spatial scales. Asset and network data add an important structural dimension to leakage analysis. Information about pipe material, age, diameter, and network topology helps explain why certain areas are more prone to leakage. Combining operational data with asset data enables more accurate interpretation of analytical results and supports targeted intervention planning. Data-driven leakage detection depends on the availability of reliable data sources and effective data collection mechanisms. Sensors and smart meters are key components of modern water networks, providing continuous or high-frequency measurements of flow, pressure, and consumption. SCADA systems play a central role in collecting and managing operational data. These systems enable real-time monitoring of network conditions and support centralized control of infrastructure elements such as pumps and valves. SCADA data provides valuable insight into how the network behaves under different operational conditions. GIS and asset databases complement operational data by providing spatial context. Infrastructure assets and their attributes are stored and visualized within GIS, allowing operational measurements to be linked directly to specific network locations. This spatial integration is essential for accurate analysis and effective intervention planning. The effectiveness of data-driven leakage detection depends heavily on data quality and reliability. Incomplete or inaccurate measurements can lead to incorrect interpretations of network behavior and reduce the reliability of analytical results. Ensuring that datasets are validated and consistent is therefore essential. Temporal resolution refers to how frequently data is collected. Low-frequency data may mask short-term anomalies or delay the detection of leaks. High-resolution data, particularly from sensors and smart meters, enables earlier identification of abnormal patterns and supports more timely interventions. Poor data quality can result in false alarms or missed leakage events. These outcomes not only reduce confidence in analytical tools but also lead to inefficient use of operational resources. Maintaining high data quality is a fundamental requirement for effective data-driven leakage management. The temporal resolution of data significantly affects leakage detection sensitivity. High-resolution data, such as 15-minute intervals, enables early anomaly detection, while aggregated daily data may conceal gradual losses. In addition, meter accuracy and sensor calibration directly influence reliability, making data validation essential in analytical workflows. Geographic information systems play a central role in data-driven leakage detection by enabling the spatial integration of diverse datasets. Flow, pressure, and consumption data gain meaning when they are linked to specific locations within the water network. GIS provides the framework needed to connect these measurements to pipes, junctions, and service areas. GIS also supports an understanding of network topology. By representing upstream and downstream relationships, GIS helps analysts interpret anomalies more accurately. For example, abnormal flow detected at one point in the network can be traced spatially to identify potential leakage zones. In addition, GIS enables advanced spatial analysis techniques that support leakage detection. By analyzing patterns across zones or acid groups, utilities can identify areas that are more prone to leakage and prioritize further investigation. This spatial perspective is essential for transforming raw data into actionable insights. Baseline and expected consumption modeling is a key step in data-driven leakage detection. Normal demand patterns describe how water consumption typically behaves over time, including daily and weekly cycles. These patterns often differ between residential, commercial, and industrial users. Reference baselines are established using historical consumption and flow data. By analyzing past behavior, utilities can define expected consumption levels under normal operating conditions. Seasonal variations, such as increased summer demand, must also be considered when building reliable baselines. Once a baseline is defined, current observations can be compared against expected values. Significant deviations between observed data and modeled consumption may indicate abnormal conditions, including potential leakage. This comparison helps narrow down areas that require further investigation. Establishing an accurate baseline requires historical pattern modeling and seasonal adjustment. Demand segmentation between residential and non-residential users improves estimation accuracy. Without a robust baseline, anomaly detection may generate false positives or overlook slow-developing leaks. Minimum night flow analysis is a widely used technique in data-driven leakage detection. MNF refers to the minimum level of flow observed in a network or DMA during nighttime hours when legitimate water consumption is at its lowest. During nighttime periods, demand is relatively stable and predictable, especially in residential areas. This makes it easier to distinguish between normal consumption and abnormal flow caused by leakage. As a result, MNF provides a useful baseline for identifying background leakage. Interpreting MNF results involves analyzing both absolute values and trends over time. Elevated or increasing minimum night flow levels often indicate the presence of leakage. By monitoring MNF patterns, utilities can detect potential leakage issues early and prioritize further investigation. Minimum night flow analysis is based on the assumption that legitimate consumption is minimal during night hours. By estimating legitimate night use and subtracting it from measured inflow, analysts can approximate real losses within a DMA. Trend comparison over time provides a performance indicator rather than a single static measurement. Anomaly detection focuses on identifying abnormal patterns in water network behavior that may indicate leakage or operational issues. These anomalies often appear as unexpected changes in flow or pressure that deviate from established baseline conditions. Threshold-based approaches use predefined limits to trigger alerts when measurements exceed acceptable ranges. These methods are simple to implement and provide fast detection, making them useful for operational monitoring. However, they may miss subtle or slowly developing issues. Trend-based detection methods analyze changes over time rather than relying on fixed thresholds. By observing gradual increases in flow or pressure anomalies, these methods can identify slow-developing leaks that might otherwise go unnoticed. Combining different detection approaches improves the reliability of data-driven leakage detection. Once anomalies are detected, the next step is to localize potential leakage areas within the network. Leakage localization techniques aim to narrow down the search space by focusing on zones that exhibit abnormal behavior according to analytical results. DMA-level analysis plays an important role in this process. By comparing flow and pressure patterns across different DMAs, utilities can identify areas with unusually high losses or abnormal trends. This comparative approach helps prioritize which areas should be investigated first. Leakage localization supports field investigations by guiding inspection teams toward high-risk sections of the network. By reducing the size of the area that needs to be examined, utilities can save time and resources while improving the effectiveness of leak detection activities. Detecting potential leakage is only valuable if analytical results can be translated into effective operational actions. This step involves converting insights from data analysis into concrete tasks that can be carried out by field teams. Prioritization plays a key role in intervention planning. Not all detected anomalies require immediate action, and resources are often limited. By focusing on areas with the highest leakage impact or risk, utilities can allocate resources more efficiently. Risk-based decision-making helps balance urgency with operational constraints. Factors such as potential service disruption, asset condition, and network criticality are considered when deciding where and when to intervene. This structured approach ensures that analytical insights lead to practical and effective outcomes. Intervention planning should be structured using a priority logic that considers impact, feasibility, and risk. Decisions must balance capital investments such as pipe renewal with operational strategies like pressure adjustment. A data-driven framework ensures that interventions are both technically justified and economically efficient. Intervention planning requires clear criteria to determine where and how resources should be deployed. One of the primary criteria is leakage severity, which refers to the estimated volume of water being lost and its impact on overall network performance. Higher losses generally justify higher intervention priority. Asset condition and age are also critical factors. Older pipes and components are more likely to fail and may require proactive intervention even if current leakage levels appear moderate. Historical failure records provide valuable insight into asset vulnerability. Operational constraints must also be considered during planning. Factors such as accessibility of network sections, traffic conditions, workforce availability, and budget limitations influence the feasibility and timing of interventions. Effective planning balances technical priorities with practical constraints. Performance indicators such as leakage per connection or leakage per kilometer allow standardized comparison between DMAs. While detailed hydraulic modeling is outside the scope of this course, conceptual reference to performance indices strengthens prioritization logic. GIS-based intervention planning adds a spatial dimension to decision-making in leakage management. By mapping analytical results, utilities can visually identify high-risk leakage zones and prioritize intervention areas based on their spatial context within the network. Scenario mapping allows different intervention options to be visualized and compared. For example, utilities can assess how intervening in one section of the network may affect surrounding areas or overall system performance. This spatial comparison supports more informed and transparent decision-making. GIS also supports maintenance planning by aligning leakage interventions with scheduled maintenance activities. By integrating spatial analysis with operational planning, utilities can improve coordination between teams and increase the efficiency of intervention efforts. Monitoring intervention effectiveness is essential to evaluate whether planned actions achieve the desired outcomes. One common approach is before-after comparison, where network conditions such as flow and pressure are analyzed before and after an intervention. This comparison helps determine the direct impact of corrective actions. Key performance indicators, or KPIs, are used to measure success. Typical KPIs include reductions in leakage volume, stabilization of pressure levels, and improved overall network performance. These indicators provide objective evidence of intervention effectiveness. Monitoring results also support continuous improvement. By analyzing outcomes and incorporating feedback, utilities can refine detection methods and adjust intervention strategies. This iterative process helps improve long-term performance and supports sustainable water loss management. Effective data-driven leakage management depends not only on analytical tools but also on organizational workflow. Coordination between analytics teams, operational staff, and maintenance crews is essential to ensure that insights are translated into action. Clear roles and responsibilities help avoid delays and miscommunication. Data feedback loops play a key role in improving analytical accuracy. Results from field investigations and interventions should be fed back into analytical systems to validate assumptions and update models. This continuous feedback improves both data quality and analytical performance over time. Operational integration ensures that data-driven approaches are embedded into daily workflows rather than treated as isolated activities. When analytics support routine decision-making, utilities can respond more quickly to emerging issues and manage water losses more effectively. Despite its advantages, data-driven leakage management faces several challenges. Data gaps and uncertainty are common issues, particularly in networks with limited sensor coverage or incomplete consumption and asset records. These gaps can reduce the accuracy of analytical results and increase uncertainty in decision-making. Technical and organizational barriers also affect implementation. Integrating data from different systems such as SCADA, GIS, and billing platforms can be complex. In addition, limited analytical capacity or lack of appropriate tools may prevent organizations from fully leveraging available data. Change management is another important challenge. Transitioning from traditional operational approaches to data-driven workflows often requires cultural change, training, and capacity building. Addressing these challenges is essential for the successful adoption of data-driven leakage management practices. Data-driven leakage detection is widely applied in urban water utilities to support continuous monitoring and targeted interventions. By analyzing flow, pressure, and consumption data, utilities can identify leakage-prone areas and focus resources where they are most needed. Scalable implementation is a key advantage of data-driven approaches. Utilities often begin with pilot areas or selected DMAs to test analytical methods and workflows. Successful practices can then be gradually expanded to cover larger portions of the network, reducing risk and improving adoption. Data-driven leakage management is most effective when integrated with pressure management strategies. Combining analytical insights with pressure control enhances the overall effectiveness of water loss reduction efforts and supports sustainable network operation. This course highlighted the importance of data-driven approaches in leakage detection and intervention planning. By using data rather than relying solely on reactive field inspections, utilities can identify leakage issues earlier and manage them more proactively. GIS-based integration plays a critical role in this process. Linking operational data to spatial network information improves the accuracy of analysis and enables targeted, location-specific interventions. This spatial perspective enhances both efficiency and decision-making quality. Data-driven leakage detection also contributes to sustainable water management. By reducing non-revenue water and optimizing intervention efforts, utilities can improve operational efficiency, protect infrastructure, and enhance long-term system resilience. This course focused on analytical methods and planning approaches for data-driven leakage detection. These methods form the foundation for applying leakage management techniques in real-world operational settings. In the next course, learners will explore a practical case study focused on DMA analysis and pressure-based leakage reduction. The case study will demonstrate how analytical concepts are implemented in practice and how results are measured and evaluated. Together, courses 421 and 422 provide the theoretical and analytical background needed to understand the real-world application presented in course 423. This progression reflects the workflow commonly used in modern water utilities, from foundational concepts to data-driven analysis and finally to operational implementation.